audible? Good evening. Okay, great. Right? So today I am going to discuss a little bit on Navier-Stokes equation solution. Navier-Stokes equation. So this is the most toughest and complicated part of the fluid dynamics, right? So, and actually as part of UPSC, if you consider, so I think only once it was asked till now, and it was very rarely it is going to be asked because the complexity is very, very high. Got it? This is almost like a research level. So this one, right, so I don't suggest to prepare this particular topic, and then I feel like actually you can ignore this particular topic. But for the sake of completeness, I am going to discuss that. So this is applicable for the viscous flow. So viscous flow meaning if there is a viscosity, right? So that means viscosity we mean there is a shear stress in the flow of water. That means if you see the grease, right? So grease actually, that is also a liquid, but the flow is very, very slow, or actually it is almost zero kind of speed, right? So the nature of that particular flow is coming just because of the nature of the fluid, that is the viscosity. Got it? So here, so in case of viscosity flow, Navier-Stokes equation plays the critical role. So what is this Navier-Stokes equation is? So just actually we can just write the Navier-Stokes equation. What it says is the material derivative dq by dt is equal to minus del p by rho, or f minus del p by rho plus del square q. So this is the Navier-Stokes equation. So this is the material derivative of the velocity, and this is the external force component. So this is external force component, and this is the density of the fluid. Density of the fluid, and then P is the pressure. So P is the pressure and Q is the velocity. So this is very complex equation, very, very complex equation. Why? Because there are some components like del square is involved, and on top of that Q is a vector. So Q being the vector, and here also Q being the vector, this has to be divided into x component, y component and z component, or Q is nothing but ui plus vj plus wk. Now if you write this particular one in this particular equation, the equation will be of two lines, very big equation. So rather than writing all the equations, what we do is we will separate the equation into the I component, j component and k component separately and write. And this is nothing but the material derivative. So material derivative actually I have explained during the starting of the class. So that will be given as, so dou q by dou t, plus q dot del q. So this is the material derivative. So this is the equivalent to this one, right? So if you replace this material derivative with this one, and the right side part also is this one, and f is also involving the component like fx into I plus, fy into j plus, fz into k. So these are the force components, or the external force components that are acting on the fluid. So these are nothing but the gravitational force, or actually any external pressure that is applied, or because of air, or actually because of presence of some weight on the fluid. So these force components that comes into picture. But usually the flow, that's what we are going to analyze, is ignoring this external force component. And then if you write this equation separately, this is going to be, for a steady flow, it will be with respect to dt, it is equal to 0. Got it? Now here, we will just write the, so take the case of a two-dimensional two-dimensional flow. Now actually in the two-dimensional flow you can think of, and then assuming there are no external force component, no external force component, then the continuity equation will be dou u by dou x plus dou v by dou y equal to 0. So this is the subject two-dimensional flow, right? So now actually this particular material derivative, if you write it in the u alone, that is this q involves u, v and w. If we write this u alone, then this can be written as dou u by dou t plus u into dou u by dou x plus v into dou u by dou y. So this is assuming two-dimensional flow, which is a material derivative. Okay, sorry. So in the Navier-Stokes equation, there is some component mu here. Just note down this. So this is the viscosity. So viscosity, right? Now here, yeah, see this. So this is the continuity equation. This is the equation number 1. Then writing the equation for the velocity component of u alone for this entire equation, assuming there are no force components, then this can be written as this is equal to 0 minus dou p or 1 by rho times of dou p by dou x plus mu times of dou square mu by dou x square plus dou square mu by dou y square. So this is the force. So this is the Navier-Stokes equation for a two-dimensional flow. Got it? So this is the material derivative component, and this is the pressure component. This is the external force component. This is the viscosity, and this is the del square phi, del square of un. Similarly, you can write for the force velocity component v. So if you write it for v, then this will be dou v by dou t plus u times of dou v by dou x plus v times of dou v by dou y, and this is equal to 0 minus 1 by rho times of dou p by dou x plus mu times of dou square u by dou x square plus dou square v by dou y square. So this is the Navier-Stokes equation for a two-dimensional flow with no external components. Now these equations needs to be solved to find out any viscous flow. Got it? So this is our analysis is limited to a lower extent by assuming there are no force components, external force components. That is one assumption. And another is our flow is only two-dimensional, not a three-dimensional flow. That is another assumption. And further, actually, we are going to even assume one more assumption. That is, the flow is steady. Steady means with respect to time, it's not going to change. The location, wherever the particle that is present, with respect to time, if there is no change in the velocity, then we say that it's a steady flow. Now, this component also, we will make it to 0. Now, and then, even if we assume, if it is only a single dimensional flow, this V component also we will make it to 0. First, you note down this, then actually we will take one particular case of Navier-Stokes equation, exact solution. Just note this now. Then, okay. Now let us take one kind of flow. So let us say there is a plate like this, and there is a plate like this. Let us say this is the ground, and then this is the y-axis, and let us say this is the x-axis. So this is the x-axis, and then velocity is in this direction with a velocity of u. Let us say if there are no velocity components along the y direction and the z direction. So this is the y-axis. Then if the fluid is flowing in such a manner that at the bottommost point zero velocity, so this is y equal to 0 and this is y is equal to y naught. So at y is equal to y naught, the velocity u is equal to capital U, let us say. And then at y is equal to 0, the velocity u will be 0. Why? Because see this is a viscous flow. So viscous flow. So this viscous flow, what it happens is, it will allow the fluid to flow in such a fashion that actually it will go in a laminar manner. Laminar means one on top of the other. Suppose take these two chalk pieces together. These two chalk pieces, if you notice, if this chalk piece is moving on top of the other, so these two are two different layers. So these two layers are actually flowing together, and then with respect to one layer, there will be another layer which is moving. Now, this flow is happening in our regular life. That is, if you see a canal, so at the bottommost point of the canal, there won't be any velocity component at the bottommost part of the canal. And at the topmost part of the canal, if you see the water on the periphery or the topmost point, there will be a velocity that is uniformly going there. In between, if you notice, there will be a velocity, but the velocity will be definitely lesser than the topmost velocity. Correct or not? That is the usual case, whatever you notice in case of any canal, right? So that kind of flow is happening just because of the viscosity of the fluid. So that viscosity will cause the fluid to flow in a laminar fashion. So this is what we are going to analyze is the laminar flow. So in case of laminar flow, so the flow will be on layers. On layers. So one layer of fluid on top of another. On top of another. So this is what we call as the laminar flow. So that means if there is a fluid like this, so this is like this, actually the fluid will move. Now this velocity part will be very, very less. At the bottommost point, the velocity will be 0. Will always be 0. So which is in contact with another surface. Which is in contact with the surface. So that's the reason actually at the bottommost point of the canal, if you notice, there won't be any fluid flow. It will just touch and stays as is, right? So that part we call as the no slip condition. We call it the no slip condition. Now, in this particular case, let us say if this is y-axis and the flow is along the u direction, that is the x direction, if there is a flow, then our Navier-Stokes equations will be reduced to a greater extent. So, assuming the steady flow. Assuming the steady flow, then our Navier-Stokes equation will be, so u is equal to 0, w is equal to, anyway we have not considered, that is also 0. And then the continuity equation, dou u by dou x plus dou u by dou v by dou y equal to 0. But this part will anyway 0 because there is no variation of the velocity along the y direction. So this part will be 0. It implies dou u by dou x is equal to 0. So if dou u by dou x is equal to 0, then it will be the integration. So dou u or u is equal to some function of y comma t. So for a steady flow, it will be only u of y. Because you are doing the derivative with respect to x, if it is vanishing, that means this is independent of x. So it may be a function of y or t. Now, t also you are taking as independent y because we are assuming the steady flow. Now, in the steady flow, what we are going to get is u is a function of y alone. This is one important thing. So, this is u of y. So, meaning u is a velocity of, is a function of y alone. What it means for us? So, u is nothing but the horizontal velocity. This horizontal velocity, as you move from the bottom to the top, so this is going to be changing. So that's why it's a function of y. So as you move from bottom to top, there is a change in the value of y. But correspondingly, the velocity, whatever is here, is not exactly equal to the velocity at this particular point. And this will be further changing like this. So as you move along y direction, the velocity is going to be changed. This is one important thing you need to notice. And then the material derivative on the left side, which contains dou u by dou t is anyway 0 because it is a steady flow. And then dou u by dou x, and dou u by dou x actually from this continuity equation we proved that it is going to be 0. And then dou u by dou y, so that is also being 0 because see this. So Navier-Stokes equation, dou u by dou t plus u times of dou u by dou x plus v times of dou u by dou y, right, is equal to minus dp by rho times of mu dou square u by dou x square plus dou square u by dou y square. So this is equation number 1. And similarly, the second Navier-Stokes equation is dou v by dou t plus u times of dou v by dou x plus v times of dou v by dou y is equal to minus dp by rho 1 by rho times of, so dou p by dou x, dou p by dou y plus mu times of dou square u by dou y square plus dou square u by v by dou y square. So this is the Navier-Stokes equation. So this part will equate to 0, and dou u by dou x is also 0, and dou u by dou y also is 0, and this part actually it will be coming out to be 0. First you note down this. I am going to erase it and then explain. Noted? Okay. Now in this equation, if you further simplify it, what we are going to get it is so here being steady flow, dou u by dou t equal to 0, dou v by dou t equal to 0 as it is steady flow. And the second one is dou u by dou x is equal to 0 from continuity equation. From continuity equation. And then v equal to w equal to 0. So assume only u velocity. So only x component of velocity is there, no y component or no z component of velocity. Now if you replace all these conditions in this equation, so this part will be 0 and this part will be 0 and this v is 0, and so entire left hand side is equal to 0, and that is equal to minus 1 by rho times of dou p by dou x, dou p by dou x plus mu times of, so dou u by dou x is 0, then mu times of dou square u by dou y square will be there. And then coming to the second equation, dou v by dou t is equal to 0 because it is a steady flow. And then so dou v by dou x is 0. And then v into dou u by dou y. So this is also equal to 0. So again, the second equation will become minus 1 by rho times of dou p by dou y plus. So here actually, so v being 0, this part will be 0. And then here also dou u by dou y. Dou v by dou x is equal to 0. Then dou square v by dou x square is also 0. Then this will be completely 0. So this is the most simplified form of the Navier-Stokes equation. Got it? Understood or not? So from this, here actually dou p by dou y equal to 0. This is one equation. And then from this, mu times of dou square u by dou y square is equal to 1 by rho times of dou p by dou x. So this is the first equation. So this is equation number 1 and this is equation number 2. So these two equations together, how is 0? So our flow or the analysis, whatever we are going to make it, right? So this is assuming to be the velocity is only along the x direction. So there is no velocity component along v direction or w direction. Understood, Samrin? That is the case of analysis what we have considered is assuming v and w equal to 0. So these are the fundamental equations for the analysis of a viscous flow which is going in only one direction. So this is a viscous flow going in only one direction with no external force component and being it a steady flow, and then no velocity components along y or z direction. So if you limit our discussion to such an extent, then these are the governing equations actually which will be useful for us solving the viscous flow equations. Got it? Understood or not? Now here actually from this relation dou p by dou y is equal to 0. Now which means p is an independent of y. So p will be definitely a function of x alone. Then it will be, so being dou p by dou x is equal to 0, then integration of this p will be function of x comma t. So as it is a steady flow, then you have to treat this as p of x, steady flow. Got it? So what we have got to is u is a function of y and then p is a function of x, and then these two values will be useful in solving this particular differential equation, which will be useful for us in identifying the flow condition in case of viscous flow with the help of Navier-Stokes equation. Got it? Understood or not? Now from these equations, if we solve this particular differential equation, what we have got? So this differential equation what we have got is mu times of dou square u by dou y square is equal to 1 by rho times of dou p by dou x. Now dou p by dou x can be replaced with dp by dx because p is anyway function of x alone. That's what we proved here from this second equation. So dp by dx. So that is the one actually which you need to understand. Then okay, so one small correction in the Navier-Stokes equation. So this is dq by dt is equal to f minus del p by rho plus mu times of del square q. Now actually this is not mu, so this is mu rho. It's not mu, so mu by rho. Yeah. So this is the Navier-Stokes equation. Then actually, so here actually, if you consider this mu being mu by rho, then actually, so this is mu by rho. So this rho and this rho will cancel, and mu times of dou square u by dou y square is equal to dp by dx. So if you integrate this, this is dou square u by dou y square is equal to 1 by mu times of dp by dx. Which one you wanted me to repeat? Samini? See this, here actually we have got two different equations. One equation is mu times of dou square u by dou y square is equal to 1 by rho times of dou p by dou x. Now here dou p by dou y equal to 0. Now dou p by dou y is equal to 0, which means for us the derivative with respect to y being 0, it can be a function of x alone or which is independent of y. So x and t. So it is independent of y. That means it may be a function of x or it may be a function of t. Now if you, it's function of t. If you assume if it is a steady flow, then it has to be independent of t also. Then it is p of x. So p is a function of x alone. That means in this equation, dou p by dou x we are writing assuming that p may be a function of x comma y. But here we proved that it is a function of x alone. That means dou p by dou x can be replaced with dp by dx. That means there will be a change in the pressure only along the x direction. Got it? So dp by dx. Now here actually if you integrate on either side, this will be dou u by dou y is equal to 1 by mu times of dp by dx into y plus c or plus b or a. Okay. Then if you further integrate it, so u is equal to, so u is a function of y, we proved. So u of y is equal to 1 by mu times dp by dx into y square by 2 plus ay plus b. So this is important for us. Got it? Right? So this is just an integration. With a lot of assumptions actually we came to this particular condition. Now here if you notice this what we are going to analyze. Now if you notice u is a function of y. So u is a function of y means there will be a change that is happening along the y direction. That means u may be 0 here, maybe some 10 kilometers per hour here, 50 kilometers per hour here, and it may be the highest velocity at the topmost point, right? So that is dependent on y. So this is a function of y alone. And then there is one dp by dx component. So this dp by dx component will mean if there is a low pressure at this particular side, then the flow will be happening along this particular direction. So here actually there are two different aspects actually that are controlling this particular flow. So one aspect is the pressure on the other side. So if it is a low pressure, then actually it will attract the fluid or it will be created vacuum at this point and then the flow is moving in this direction. Suppose if it is a high pressure, then the flow will be driving onto the other side. Now in certain cases what is happening is the flow will be reversed at this particular point at the bottommost point and the flow will be this direction at the topmost point. Got it or not? So this usually happens actually in the deep sea level. So where the topmost layer is flowing in one direction and the bottommost flow is happening in the other direction. So this kind of cases can occur in the deep sea. So where there is a component of dp by dx here and there is a component of y here. Now these two together will decide how the flow has to happen in this particular case. Now if there is a fixed plate here and if there is a movable plate, or movable plate we mean if there is a topmost flow layer that is happening on this one, in that particular case we call as one condition, that is the flow is purely if it is due to only because of the flow at the topmost layer and without having any pressure gradient. In such cases we call as plain Corti flow. So plain Corti flow means, so flow is only due to the flow movement of the top layer. Only due to the movement of the top layer. And then suppose if the flow is only because of, that is only because of the pressure gradient, then we call as Poisson flow. So you can note down this. So once you note down this, then I'll write the definitions. Note it down? Okay. If the flow is only due to the movement of top layer of the fluid, then we call as plain Corti flow. If the flow is only due to pressure gradient, that is dP by dx not equal to 0. So here actually dP by dx equal to 0. So in this case, where dP by dx not equal to 0, we call the flow as plain Poisson flow. If the flow is due to both then we call as generalized Corti flow. Generalized Corti flow, right? So these are the three different kinds of flows actually that are going to be analyzed with the help of Navier-Stokes equation with lot of assumptions whatever we can make. Got it? Understood? Any questions? Note it down. Okay. So now here actually the differential equation that will be u of y is equal to 1 by 2 mu dP by dx y square plus a into y plus b. So this is the differential equation which will give the velocity at any point. Now this velocity, if you notice, the horizontal velocity which is dependent on y and which is dependent on the dP by dx component. So dP by dx actually will create, or actually if it sucks here, that means if there is a vacuum it is going to, if it is having more pressure, then actually it is going to pull on the other side. Now here, so assuming that dP by dx is equal to 0, that means plain Corti flow. In that case, this will be straight away so in plain Corti flow, dP by dx equal to 0. If this is 0, then what we have left is u of y is equal to ay plus b. So this is the simple most equation. Now this is as if like if the bottommost point, right? So this one, if it is having certain velocity component of b, then it will be linearly increasing from bottom to top. Now actually, assuming that if there is a no slip condition at the bottom, that means at y is equal to 0, u is equal to 0. At y is equal to y naught, u is equal to capital U. Then substituting the initial condition will lead to u at any instant of y. So the condition v will be becoming 0 based on boundary conditions. So based on boundary condition, so u is equal to 0, a into 0 plus b. So it implies b is equal to 0. And another condition is the topmost velocity is u at a distance of y naught plus b. So this is b is anyway 0. It implies a is equal to u by y naught. That means the original equation u of y is equal to a into y by y naught. A is u by y naught. So this is the velocity. So that means u of y is directly proportional to y. So this is what we call as the planar flow or the laminar flow. Got it? So this is the plane Curtis flow equation. So plane Curtis flow means it is linearly increasing. As we go on to the top, the velocity component, which is 0 at this point, it is keep on increasing and reaches to a final value of capital U. So at any instant, if you notice, there will be a different velocity. Got it? In the plane Poiseuille flow, wherein this dp by dx actually we assume it is not equal to 0. Now if it is not equal to 0, then the boundary conditions will be, note it down. Okay. Now suppose if it is generalized Curtis flow, if it is generalized Curtis flow, then u is 0 at the bottommost point where y equal to 0. It implies b is equal to 0. 0 plus 0 plus b. So it implies b is equal to 0. And then a value, so that is at the topmost point, the velocity is u, and then 1 by 2 mu dp by dx into y naught square plus a times of y naught. And so plus b you can treat as 0. Now here, so what you are going to get is a is equal to u by y naught minus 1 by 2 mu times of dp by dx times y naught. Got it? So this is the arbitrary constant value what we have put in. Now this arbitrary constant, if you replace it here, that is u of y is equal to 1 by 2 mu dp by dx into y square plus u by y naught minus 1 by 2 mu dp by dx of y naught into y. So this is the equation in case of generalized Curtis flow. Got it? So I have divided with y naught. That's why actually the square became y naught. Yeah. Got it? Understood? Okay. So this one, finally, this form, right? So you can simplify and then finally put it into a most simplified format. That simplified format, what we have to got is, that is u of y divided by capital U is equal to y by y naught minus y naught square divided by 2 mu u dp by dx into y by y naught into 1 minus y by y naught. So usually this is treated as minus of this is treated as plus. So plus p. So p is equal to minus y naught square divided by 2 mu u dp by dx. Then u of y divided by u is equal to y by y naught plus p times of y by y naught into 1 minus y by y naught. So this is the actually standard format usually it is put in. Now why we are putting in this particular format is this p value is nothing but minus of, so this value is the p. Now here p and dp by dx. So this is some random value. So which is given by this equation. Now this is directly related to dp by dx. And then it is having an opposite sign of negative. So here what it means is, suppose if dp by dx is positive, if dp by dx is positive, that means there will be a positive pressure gradient on the other side. Or actually we take the negative first. If I say that this is, there will be a negative pressure gradient on the other side. That means as you move from this place to this place, there will be a drop in the pressure. So if it is dropped in the pressure, see this, dp by dx, right? So p actually I am reading as dp by dx here. Now this part is nothing but this p. So this is what we have got in the simplified form of the differential equation, what we have submitted the boundary condition in the previous snap. Now here, this is the final equation. This p value, depending upon the p value, you are going to get different kinds of flow, because this is the most generic flow, which we call as the plane Cauchy flow. So this will be the generalized Cauchy flow. And the generalized Cauchy flow, we have taken two different variations. One is the plane Cauchy flow, and another is plane Poiseuille flow. And this is the most generic format. In the most generic format, dp by dx value, if it is having certain value, then we call as the Poiseuille flow. If dp by dx is 0, then we call it as the plane Cauchy flow. Now here, this dp by dx value will decide the flow, whether it has to go in the forward direction or the backward direction. Now, if dp by dx is negative, then that means there will be a negative pressure gradient onto the other side. That means if you move on the positive x direction, there will be a drop in the pressure. Obviously, the flow will be accelerated just because of this pressure gradient along with the movement of the bottom to the top. Correct or not? There is a flow at this particular point. Then obviously if there is a pressure gradient, these two together will move this particular fluid onto the other side. Suppose if dp by dx is positive, the flow will be towards x, due to pressure gradient. Suppose if dp by dx is positive, then it will be, the flow is due to negative side. That means the pressure gradient is positive. If you move from here to here, more pressure is there. That means it will try to push the body like this. Right? Now, suppose if there is a plate that is moving on the top, and this plate is moving with a velocity of u, and if there is a pressure gradient which is positive onto this side, obviously the flow at the top, because of this layer movement, it is going to be right side, and due to positive pressure gradient, the flow will be on the reverse side at this particular point. Got it or not? And this will be decided by this dp by dx, indirectly by p. Got it or not? Understood? So this is what is the complete analysis with the help of Navier-Stokes equation, exact solution with the assumptions whatever we have made. That is only one-dimensional flow, another is the steady flow. One-dimensional and steady flow. And then, so this is how actually we are going to analyze with the help of Navier-Stokes equation. So this is about the Navier-Stokes equation. So if you have any questions, you can let me know. And then in UPSC, I think so only once it was asked. So none of the years actually it was asked. Yeah. So this is one of the complex level of analysis. So because from this actually we have derived to a lower extent by taking the complex form of the Navier-Stokes equation. Right? Okay. So this is about the fluid dynamics. So I hope you don't have any other questions. So you can solve the material whatever we have sent. So that is sufficient enough. Or else you can follow Rai Singhania or Shanti Swarup. So that will solve you all the problems. So that knowledge is sufficient enough. So this will be the end of fluid dynamics classes, right? So we are going to start in the upcoming class. It is fine. Okay, yeah. So thank you. So in that case, right, 5:30 to 6:30. So from Monday onwards, I am going to take it up. So only mechanics won't be much of the syllabus. So mechanics will be smaller syllabus only. Which we are going to finish it up soon. And then partial differential equations. That is almost, I think so. Many people are very much comfortable with partial differential equations. So we are going to cover that particular topic. Got it? Yeah. So that's all for today. So we are done with the fluid dynamics.